Welcome to this lesson session on rational root theorem with Was Moses, a mathematics teacher. Before you begin this lesson, click on the red button below to subscribe for more future lessons. We begin. As lesson objectives, at the end of this lesson, viewers should be able to apply the rational root theorem to find all possible real rational roots of any given polynomial equation. Determine the number of positive and negative real roots of any given polynomial function using Descartes' rule of signs. As a keynote, the rational root theorem is used to easily find at least one integral factor of any given polynomial function if it exists. In this lesson, we are also going to look at Descartes' rule of signs used in determining the number of positive or negative real roots of any polynomial function. Now, the rational root theorem statement. Let an x to the power n plus an minus 1 x to the power n minus 1 plus an minus 2 x to the power n minus 2 plus continuous right down to plus a1 x plus a0 equals 0, with an different from 0 represent any polynomial equation of degree n with integral coefficients. Now, if a rational number p over q, where the greatest common divisor of p and q is equal to 1, is a root of the above polynomial equation, then p is a factor of a naught and q is a factor of an. So we are saying that in any given polynomial equation, we look at the coefficient of the leading we look at the coordinate of the coefficient of the leading power, and we look at the constant factors p. Possible factors of p will come from. Okay, we move on. As a remark, to assist us in this theorem, we are going to look at Descartes' rule of signs. Now, René Descartes was a French philosopher and mathematician of the 16th century. In 1637, he proved a theorem on the rule of signs. And this rule of signs, he uses them to determine how many positive real roots can a polynomial have, how many negative real roots can a polynomial have, given that the polynomial equation is stated and not yet solved. So the statement of the Descartes rule of signs. Let's suppose p of x is a polynomial whose terms are arranged in descending powers of the variable x. Then the first point, the number of positive real roots of p of x is the same as the number of changes in the sign of the coefficients of the terms of p of x, or is less than this by an even number. Next, the number of negative real roots of p of x, of the polynomial p of x, is the same as the number of changes in the sign of the coefficients of the terms of p of negative x, or is less than this by an even number. Okay, please, looking at these phrases, less than this by an even number, it means that in any polynomial, when we look at the sign changes the changes in the sign of the coefficients, and they give maybe, for example, 3, we can say that either that polynomial has 3 positive real roots or it has just 1 positive real root, because it is possible that a polynomial could have real roots or complex roots. And in the case where those real roots do not exist, those real roots will be complex. And we know that for complex roots, we can never have 1 complex root. We can always have 2 or even number of complex roots, since complex roots occur in conjugate forms. Now, as a case study to the application of the rational root theorem, we'll be looking at cubic polynomials. And as a recall, a cubic polynomial is one in the form p of x equals a3 x to the power 3 plus a2 x squared plus a1 x plus a0, with a3 different from 0. That is, we are simply saying that a cubic polynomial is a polynomial of degree 3. And we need to also know that every cubic polynomial has at least 1 real root. So all the cubic polynomials, all polynomials of degree 3 must have 1 real root, at least 1 real root. In the case where the other roots are not real, we will always have 2 complex roots, because complex roots occur in conjugate forms. Application examples. Factorize the following polynomial functions using the rational root theorem. A, f of x equals x cubed plus 2x squared minus 5x minus 6. B, g of x equals 6x cubed minus 11x squared minus 24x plus 9. Hence, self-inject the set of integers, the equations f of x equals 0, g of x equals 0. Now, when we look at these polynomials, normally given a polynomial, you'll be given a trial divisor or a trial factor where you can easily use it to break down the polynomial. But in these cases, the polynomials are open and we need to factorize. In which case, when we were still in the ordinary, at the ordinary levels, we used to do what we call a try and error method. So the rational root theorem is coming in to guide us so that we know the possible values that could be used to obtain the root, not just generally substituting any type of number that we can. So as these application examples, solving the application examples, we're going to see exactly how the rational root theorem can be applied. We move on. A, f of x equal to x cubed plus 2x squared minus 5x minus 6. Solution. Using the rational root theorem, we need to bring out a0, and we said a0 is the constant number in the polynomial. So a0 is -6, and an is the coefficient of the leading term or the leading degree. So an in this case is the coefficient of x cubed, which is 1. Possible factors of -6. So we look for the possible factors of this constant of a0, which is plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Also possible values of an, in this case, possible value factors of 1. We only have 1, which is plus or minus 1. Okay, now, possible set of rational zeros. In a special case where the coefficient of the leading term in the polynomial is 1. the possible rational zeros we are going to obtain, that set will always be the set of the constant. So in this case, the possible set of rational zeros. And recall that when we talk of zeros to any given polynomial function, we mean the values of x when that polynomial is equated to 0, which is, in other words, the roots of the polynomial equation. Possible set of rational zeros, m over n is equal to the set of plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. This one is exactly the set of possible factors of -6. Why? Because the leading coefficient is 1. Okay, after obtaining this, it means that to factorize this polynomial function, if any of these numbers doesn't satisfy a 0 to this given polynomial, then the polynomial will not have any integral root. So that is what the rational root theorem is trying to tell us. So to continue, we need to also study this polynomial and use Descartes' sign rule of signs to determine how many positive roots and how many negative real roots. So the coefficients are 1, 2, -5, -6 of f of x. Now, from 1 to 2, there is no sign change. From between 2 and 5, there is a sign change, meaning one sign change. Between -5 and -6, there is no sign change. Therefore, it's possible that this given cubic polynomial has only one positive real root. And if it has only one positive real root, the other root will either be negative real roots or complex roots. Good. So Descartes' rule of signs implies one positive real root and two negative real roots. So using synthetic division on the possible set, this possible set, we have, recall that synthetic division is the lesson we did before this particular lesson. So using the synthetic division on the possible set, we have a table of possible values. We take each of these values after bringing down the coefficients. These are the coefficients: 1, 2, -5, -6. The root. We use the first root. The first root, the roots are these factors of the possible set of rational zeros. We take the first one, which is 1, 1. Carrying out synthetic division using 1, we bring down the first coefficient, 1. 1 times 1, 1. 1 plus 2, 3. 3 times 1, 3. 3 plus -5, -2. -2 times 1, -2. -2 plus -6, -8. So the last digit or the last number is always the remainder. This is the remainder column. That's why here the remainder is -8. Okay, and if the remainder is -8, it means that 1 is not a 0 or 1 is not a root. Okay, we move forward. The value that will give us a remainder of 0 gives us a 0 to that particular polynomial, and that is where we stop. We take, after +1, we use -1. Now, taking r equals -1, we bring down the first coefficient, 1. 1 times -1 is -1. -1 plus 2 is 1. 1 times -1 is -1. -1 plus -5, -6. -6 times -1, 6. 6 plus -6, 0. meaning the remainder when the root is -1 is 0. Therefore, we say that R equals 0 when x equal to -1 implies that x plus 1 is a factor of f of x with a depressed polynomial given by these coefficients, with a depressed polynomial of x squared plus x minus 6. Thus, f of x is equal to x plus 1 into x squared plus x minus 6, which is equal to, now, factorizing quadratics dissolves this one to x minus 2, x plus 3. Thus, the entire polynomial function f of x is factorized as x plus 1 into x minus 2 into x plus 3. Example 2 or B. G of x is equal to 6x cubed minus 11x squared minus 24x plus 9. We look at the solution. Again, applying the rational root theorem to this, a naught is equal to 9, which is the constant, and an is equal to 6. Possible factors of 9 are constitute the set plus or minus 1, plus or minus 3, plus or minus 9. Possible factors of 6 constitute the set plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Now, possible set of rational zeros gives the rational number m over n, which gives the set of factors coming from 9 over factors coming from 6. So the first factor is 1 over 1, which is plus or minus 1. The second is 1 over plus or minus 2, which is plus or minus half. The third is 1 over plus or minus 3, which is plus or minus 1/3, and 1 over plus or minus 6, which is plus or minus 1/6. After that, we move to the next 3. Take plus or minus 3 over 1, which is plus or minus 3. Plus or minus 3 over 2, which is plus or minus 3 over 2. Plus or minus 3 over 3, which is already there, 1. Plus or minus 3 over 6, which is already there, 1 over 2. Plus or minus 9 over 1, which is this, plus or minus 9. Plus or minus 9 over 2, plus or minus 9 over 2. Plus or minus 9 over 3 is 3, which is already there. Plus or minus 9 over 6, that is 3 over 2, which is already in the set. Good. So with this, again, we bring out the coefficients, which is 6, -11, -24, and 9, as indicated here. And applying Descartes' rule of signs, we look at this. Moving here, we have a sign change, one positive real root. Between -11 and -24, no sign change. Between -24 and 9, sign change. So meaning that there are 2 sign changes indicating 2 positive real roots or 0 positive real roots in the case where this polynomial has a complex root. The complex root and a conjugate will dissolve the positive real roots, and 1 negative real root. Now, using synthetic division on the possible set we have, using synthetic division on the positive set we analyze the coefficients and the remainder column. the root column. We start one root after the other in the possible set of rational zeros. The first is 1. We take 1 as a root. Write out the coefficients as indicated: 6, negative 11, negative 24, 9. We bring down 6. 6 times 1, 6, plus negative 11, negative 5. Negative 5 times 1, negative 5, plus negative 24, negative 25, 29. Negative 29 times 1, negative 29. Negative 29 plus 9 gives negative 20. That is, remainder is negative 20, showing that this is not a root or a zero. We bring down the next possible root, negative 1, and we test using synthetic division. Synthetic division is always necessary in that when you test using synthetic division, the one that gives you a factor already gives you the depressed polynomial, the resulting reduced polynomial. Okay, now bring down 6, which is a coefficient. 6 times negative 1, negative 6, plus negative 11, negative 17. Negative 17 times negative 1 is positive 17. Positive 17 plus negative 24, negative 7. Negative 7 times negative 1, 7. 7 plus 9 gives 16. So the remainder is 16, which is different from 0. Showing that negative 1 is not a 0. We move to the next. The next is 1/2. So the next is a half. We try a half. Bring down 6. 6 times a half, 3. 3 plus negative 11, negative 8. Negative 8 times a half is negative 4. Negative 4 plus negative 24 is negative 28. Negative 28 times a half is negative 14. Negative 14 plus 9 is negative 6, giving a remainder of negative 6, which is different from 0. We move on. We use negative half. Bring down 6. 6 times negative half is negative 3. Negative 3 times negative 3 plus negative 11 is negative 14. Negative 14 times negative a half is 7. 7 plus negative 24, negative 17. Negative 17 times negative a half is 17 over 2. 17 over 2 plus 9 gives 35 over 2, which is a remainder, giving us a remainder of 35 over 2, different from 0. Thus, we move on. We move to 1 over 3. 1 over 3. 6 times 1 over 3. After bringing down 6 again, 6 times 1 over 3 is 2. 2 plus negative 11 is negative 9. Negative 9 times 1 over 3 is negative 3. Negative 3 plus negative 24 is negative 27. Negative 27 times 1 over 3 is negative 9. Negative 9 plus 9 is 0. Remainder 0. Hence, this one has a remainder of 0. Therefore, we have had the first 0 as 1 over 3. So remainder equals 0 when x equal to 1 over 3 implies 3x minus 1 is a factor of f of x with a depressed polynomial of 6 over 3 x squared minus 9 over 3x minus 27 over 3, which is equal to 2x squared minus 3x minus 9. Now, again, why do we have to divide these coefficients in the depressed polynomial by 3? Recall the special remark that was given during synthetic division, the lesson on synthetic division, that when the linear factor or the linear divisor is in the form ax plus b, to obtain the depressed polynomial, we should always divide the resulting coefficients by the coefficient of x in the linear divisor. Good. Now, this gives us g of x to be equal to 3x minus 1 into 2x squared minus 3x minus 9. But following the method of factorizing quadratics, this quadratic 2x squared minus 3x minus 9 will be factorized into x minus 3 into 2x plus 3. Here, you need to contact quadratic factorization method. And here, it means that g of x is completely factorized into 3x minus 1, all that into, 3x minus 1 into x minus 3 into 2x plus 3. We move to C. Solve in Z the set of integers, the equation f of x is equal to 0. Now in A, we already factorized f of x. Here we just need to bring the factors of f of x, obtain, which gives x plus 1 into x minus 2 into x plus 3 equal to 0, and solve for the values of x. And here, by principle of factorization, either x plus 1 is equal to 0, or x minus 2 is equal to 0, or x plus 3 is equal to 0. Three linear factors imply 3 values of x. Making x the subject in each of these cases, we have x equal -1, or x equal 2, or x equal -3. Thus, solution in Z is such that x is equal to -1, or x is equal to 2, or x equal to -3, since all these three zeros are integers. And now, please, if we look back at Descartes' rule of signs, we stated that this polynomial, the polynomial f of x, was going to have only one positive real root and two negative real roots, actually confirming that particular theorem. So whenever you see a polynomial function, you can use Descartes' rule of signs to determine the nature of the solution before you even start solving. We move to D. Sorry, it's here, it's still written. Correct it to D. Yes, we move to D. Solve in Z set of integers the equation g of x is equal to 0. Again, in B, g of x was already factorized. We just bring the factors of g of x from g of x equal 3x minus 1 into x minus 3 into 2x plus 3. We just take these factors and equal to 0 to solve this polynomial equation. This implies that 3x minus 1 into x minus 3 into 2x plus 3 is equal to 0. And by the principle of factorization, either 3x minus 1 is equal to 0, or x minus 3 is equal to 0, or 2x plus 3 is equal to 0. Now, solving for x, here, 3x minus 1 equal to 0, making x the subject, we have x equal, send 1 this other side, divide by 3, 1 over 3. Or x minus 3 equals 0, send 3 this other way, x is equal to 3. Or 2x plus 3 equal to 0, send 3, giving negative 3, dividing by 2, we have x equal negative 3 over 2. And again, when we're analyzing this polynomial in B, we said that applying the Descartes sign of rules, this polynomial was going to have 2 positive real roots and 1 negative real root. As we have just seen, this one is a positive real root, this one is a positive real root, and this one is a negative real root. So just confirming the Descartes rule of signs. And we were asked to solve in Z, the set of integers. But looking at these solutions, you see that 1 over 3 is not an integer. Negative 3 over 2 is not an integer. Thus, the solution in Z, the set of integers, is just x equal 3, since 1/3 and negative 2/3 does not belong to the set of integers. We have come to the end of this presentation. Thank you for viewing. If you did not subscribe at the beginning, don't forget to click the subscribe button for more future lessons.